Yes, all good to go. Cool. So, hope everybody had a good weekend. Stayed relatively cool. And let's start off with any questions. Either on the homework, which remember is not due until Thursday, or the lab, which is also due on Thursday. Hold on a second, I still got audio issues. I can hear you talking, but it's using my wrong. Alright, so hold on, let me turn off my screen. Oh man, I just broke my Zoom. Alright, hold on. Alright, I think I have audio now. Go ahead and try talking again, please.
Hello?
Hello, there we go.
I had a question.
Alright, go for it.
So, this is more curiosity, but if you have one byte for the operand, one byte for an opcode, in terms of assembler for pick, at least this picture, that would be the default word size, right?
Pretty much, yeah.
So you would call that the word size? I noticed like on a bit shift calculator, it's like D word, Q word, W word.
So on the PIC processor, the word size for an instruction is 16 bits. Most instructions are 16 bits. It's technically an 8-bit processor, so you might call the word size 8. Word is not really a strictly well-defined notion. Bytes are strictly defined. Bytes are always 8 bits. But the notion of how many bits is in a word, kind of a little bit loosey-goosey. But I would say the word size for the PIC processor is probably 8 bits. But most instructions are 2 words, 16 bits, if that makes sense.
Okay.
And it's roughly 8 bits for an opcode, 8 bits for an operand. That's not exactly how it breaks out, but we can think of it that way. The opcodes are usually, 6 or 7 bits, and then there's 1 or 2 bits of additional information, the D bit and the A bit, and then there's usually 8 bits of operand.
I have a question.
Mm-hmm.
I know that reg doesn't technically, WREG, have any data inside of it. And on number 2, it asks us to increment or de-increment reg that specific file. But it's not saying that we're supposed to be using any other file outside of that to increment, to put into reg, and then put into something else.
So reg is an 8-bit register. It always has some value in it, right? It's like a flip-flop. Whether we load something into the flip-flop, whether we ever touch the clock, if you take a flip-flop and you apply power, the Q output will be a 0 or a 1. We just can't predict what it's going to be until we've done something deliberate to it. Well, the W register is the same thing. It always has a value in it. We don't know what that value is necessarily. But it's got some value in it. So question 2, increment file register 0, decrement file register 0, add 1 to register 0, but store the result in WREG. So increment register 0, but you're playing with a destination bit on that part. And then the fourth one, copy.
The last one in number 2.
Okay, increment WREG and store the result in file reg hex 10. So let's see. So we don't necessarily know how to increment WREG yet. There is a way to do that, which we'll get through today. But we do know how to move wreg into file register 10, right? That's what you did in the previous instruction. And so you could copy wreg into 10 and then increment 10 and then copy 10 back to wreg.
You could use the literal functions too, right?
You can use the literals with an add, for example, to add a number to register 10. So you can increment by 1 also by adding the literal value 1 to a register.
But isn't the point of this specific practice to increment reg and then put it into a file, not for like us to change a different file, move it into reg, and then just move it into the other file?
Well, but the end result is the same, isn't it?
Depends. The instructions were very specific, and I was wondering if, like, you don't really care about the specificity? Yeah, whatever.
Yeah, it's hard to say. Specificities, yeah. Specifics.
Thank you.
Yeah. So the way I wrote it, it said increment wreg and store the result in register 10. So that sounds like two things should be happening. Let me ask you, are you seeing my hand on my document scanner right now, or did I break my screen share?
You broke your screen share.
Oh man, okay. Because it's not letting me stop my share, even though it's not sharing. So let me try this. Let me try a new share. Okay, did that work?
You got the all clear.
Yep.
Awesome. Cool. All right. So there's a few things happening in here. So it says increment wreg, and then store the result in file register 10. So that's the goal. You want these things to happen, and you generally want nothing else to happen. So one way to do this would be to take wreg and copy it into 10, and then increment 10, and then copy 10 back into wreg. And I think if you do those three things, the result will be wreg will be one more than it was, and that incremented value will be in file register 10. So that should be one way to do it. Another way that someone suggested was you could say add literal value 1 to the W register. That increments the wreg, and then move the wreg to file register 10. So that's a shorter way to do it, shorter and faster.
If you wanted to decrement, since the integers roll over, could you add the max and minus 1 if you wanted to decrement 1?
Excellent. Yes, absolutely. So this is a interesting thing to think about. So if you want to decrement by 1, somebody said add max int minus 1. Well, if we have 8 bits, what's the maximum integer that we could represent?
FF.
Cool, hexadecimal FF. What is that in decimal?
255.
255. If we think of the world as being 2's complement, what is this thing as a 2's complement number? And this is what it looks like in binary.
Just -1.
Yeah, this is -1. If you want to know what this value is, complement all of the bits and add 1. That gives you the number 1, which tells you that this thing, before I complemented and added 1, this must have been equal to -1. So adding 255 is the same as subtracting 1 or adding -1. And that can be a useful trick sometimes. So if you want a decrement, you could actually just add 255 to something, and that would bring the value down by 1. So there's this subtract literal word instruction. And, if we say add literal word, we think of adding some, constant, some literal to the W register. Subtract literal W, what it actually does is it takes W and subtracts it from the constant that you specified. And that's a little backwards. So if we said subliteral W1, that does not subtract 1 from W. That takes 1 and it subtracts W from it. So we can't decrement W by saying subtract literal W1, but we could use add literal W, and we could add hex FF, and that would be the same thing as adding -1, which will decrement. These are tiny, picky little gotchas that can keep you up trying to find a bug in code. And you've always got to come back to the data sheet and double check all of these instructions, especially with subtracts. There's potential ambiguity which way you're going to subtract two things. So stay friendly with your data sheets. All right, let's go ahead and do an attendance ping. So send me a note with your Canvas name, dash, and the word here. Send it as a direct message, please. Let me know that you're here. Cool. And then again, if you go away from keyboard for a little bit, just send me an AFK note when you're away and send me a back when you're back. All right, cool. So let me make a general comment on Lab 1, and I've only had a couple of people ask me about this, but Lab 1, you're doing all of these experiments. You're doing all of these procedures where you create a project and you take this code and put it in, you build it. You set up stimulators, you set up watch windows, you step through, and so on and so forth. And somebody asked me, what are we supposed to put in our lab report? Well, this is an experiment. If you were in a chemical laboratory and you were mixing two solutions together, right, you would describe how much of each solution you used, and you mixed them, and you saw a puff of smoke, and your lab assistant grew a second head, and you'd record all of these things. That's basically what you want to do in these exercises, these labs that you're doing with the simulator. So for example, you're supposed to set up some watches on these locations, and then you're supposed to set up a stimulus which lets you toggle an input pin. We're going to talk about what this actually is doing today. And then you're going to step through the simulation by hitting F7 or by hitting the step button in the simulator window, and so on and so forth, right? So you should be seeing certain things happening as you do this. What you should find is that as you step the simulation, certain things happen, and then it goes into a loop. And it just keeps executing a relatively small chunk of code. And then when you hit this stimulus, and you step the simulation after that, you'll see it go into a different set of code. And something will change, and then it'll go back to that first set of code and loop there until you hit the stimulus again. And then when you hit the stimulus again, it'll go down to that new section of code again, change something again, and then go back to that first section. So all of that you observe, right, you want to understand what this system, what its behavior is. right? And we're not digging yet in this lab into why it's doing this, but you want to observe what the behavior is and you want to document that. So how do you document it? Well, you can describe it in words. You can take screenshots, right? And I asked you not to do a screenshot for the disassembly listing, but for outputs from the simulation itself, screenshots work great. So if you've got a watch window where you're looking at the values of these locations, and then when you stepped, to this line, the value in this location changed, right? Take a screenshot of that and describe it, right? Put that screenshot in the report, and then, right before or right after it say, when we stepped one more instruction, we saw that this location changed from this to that. And then it stayed the same until we fired the stimulus again, right? So think of it as a laboratory experiment. Think of it as, something you're observing under a microscope. You apply a stimulus and there's a behavior that comes out of that. That's the kind of thing you want to think about in terms of what do you put in your lab report. And it'll be a little more obvious in the future labs when you're actually writing your own code, because you're going to be trying to get some particular behavior out, and so that's what you're going to describe when your code is working. But here it's just kind of an exploration. We've typed in all this stuff, we've clicked all these weird things, and now we're observing what happens. All right. Any other questions, issues?
I have one.
Sure.
For the new experiment section, I don't really know what to do for that part. Are there any recommendations or
My
directions I could possibly go?
Yeah, so one idea is, we're going to be using this software tool a lot, and we don't, necessarily know a lot of coding right now in assembly language, but you've got a project in here and you compiled it, and you did some stepping of it, and so on and so forth, right? But there's a lot of buttons, there's a lot of options, there's a lot of things you can do in here. In the stimulus window setup, you're setting one option, which I think is for toggle, but there's other options. There's a pulse option, there's a set high, there's a set low. You could explore, what one or two of those options do. This whole display is tabbed and windowed and reconfigurable. For example, my variables right now are showing up here. My output window is showing here. My source code is here. Well, if I take my source code and I grab that tab and I bring it down like this, I can split my display. So now I have source code here, and here I have my tabs down here. And maybe I want to see my variables while I'm running, so I can grab that variable tab and I can put it right there. And now I can look at my output and my source code and my variables. And so, just playing around with the tool itself, with the IDE is, could be a whole new experiment, right? So my suggestion would be maybe just do some exploration with the tool itself. Do some things along the lines of what we did in the experiment, but try some different things maybe. Pretty much anything you can think of, and then just write it up as a new experiment. Does not have to be very fancy. Okay, it's really just, spend some time finding something new, right? What are these things, these little dots over here? If I click on that, what does that do? Well, I don't know, it doesn't seem to do anything. But if I right click on something, does that do something? I may have broken my simulator actually, but on some of these you can click on a variable, you can change the format in which it's displayed. Let me see. Yeah, I broke my MP lab. Or make an experiment where you try to break MP lab.
That sounds like fun.
That does sound like fun. Probably pretty straightforward to do from my experience.
Speaking of trying to break things, I actually was trying to set port A so that I could use more than one bit
Mm-hmm.
for my second experiment.
Okay.
I tried manipulating what I believe the value of trisa, the literal right above it, and seeing if that would do it, but I guess that's just for direction only.
So we're gonna talk about trisa and port A today. It's potentially confusing a little bit as to what's going on.
Memory mapping?
It's not as bad as memory mapping, but it's a different way of thinking about things. So we're going to talk about this business with adcon and tris and port. We'll get through that today and or Thursday. But you're absolutely right. You have to play with trisa in order to be able to do input on more than one pin. Let's see. I use the locations from lab 1 to do my new experiment, and it works. But do I need to change those? No, that's fine. You can reuse memory locations. Totally. All right. Yeah, MP Lab is not happy with me, so.
Can you do x86 assembly in MPLAB?
No, you can't. It's strictly for microchip, which is their own assembly language. But if you have Linux, right, you can use GCC or you can use AS to do x86 assembly, and you can use GDB to debug it. And you can compile code written in C, like in GCC, and you can say -S, and that will actually convert your C code to x86 assembly and leave you the assembly language file, and then you can go ahead and you can play with that and edit it and then assemble that and then execute it. So x86 development's pretty easy to do tool-wise, particularly if you're on Linux. But MPLAB doesn't do that. All right, I fixed my MPLAB. I still have a camera, good. All right, so homework 2 is due a week from today. Remember last week I said homework 1 was pushed until Thursday. So homework 1 is due Thursday. Lab 1 is due Thursday. Labs are always due on Thursday. Homeworks are generally due on Tuesday. So homework 2 will be due on Tuesday, and we'll go through most of what you need today to be able to do homework 2. So that's something to start looking at. I pushed homework 1 last week because I wasn't sure we were going to get far enough to get it done today. It turns out actually we did, but got a little extra time on it. So. All right. Let's see what I got. So let's dig deeper into the architecture of this PIC processors. So I told you last week that there are 256 general file registers, places where we can store information. And we've been using these ideas of 8-bit operands. So in your instruction maps, there's usually these 8 things called F, which is usually an 8-bit operand address. So for example, increment file register, if you look at the coding for it, it's a pattern of 6 bits. It's 2 bits for the D and A bit. And then there's 8 bits that specify the address of the operand, right? The location of the file register you want to increment. And since we have 8 bits, we have 256 file registers. And in hex, there's 00 through FF. But there's actually more than that. There are about 100 some other file registers that we can also work with. And they're not general purpose file registers. They're what are called special function registers. And so let me pull up a data sheet for this. So I'll go with a quick guide. So I've got them at the end of this shortened data sheet. So table 5-2, register file summary. And these are registers with peculiar names: TOSU, TOSH, TOSL, stack pointer, PC latch, upper, higher, PC latch. But also in here you'll find things like port A and port B and trisa and trisb, things that we saw in that code for lab 1. These are file registers in the same sense that, you know, these file registers we specify when we say, you know, increment file register. Same idea, but they're somewhere different inside the processor. And they're not general purpose registers. We can't just use, you know, port A or OSCTune to hold, you know, a counter or something like that. These have very specific purposes. And a big part of this course, a big part of using the PIC processor or any similar processor is understanding these special function registers. And, you know, most processors have a ton of these special function registers, and so this is a version of memory mapping, right? We can refer to things at different addresses, and instead of being a location in our memory, they tap into pieces of the hardware. So here's a numbered list that shows just the name of each of these special function registers and its address. And this is where we start to see these 3 hex digit addresses: F80, F81, FFF. And so this raises a question. We've been talking so far about 8-bit operands. We've been specifying our file registers with 8 bits. But all of a sudden we have these registers that look like they have 12-bit addresses. And so we're going to, you know, reveal the truth about how these file registers are set up, and this gets a layer of complexity added to what we've been doing so far. And so the reality is that all of our file register addresses are actually 12 bits. Alright, so when we specify an operand, the CPU is actually thinking of our operands as being 12 bits to specify an address, not just 8. And so we can start to make what we can think of as a memory map. And anytime you start working with a new processor, and this is the only processor we use in this course, but you know, if you start working with a different processor somewhere, find a memory mapper, make yourself a memory map for how it's laid out. So here's what a memory map might look like for our PIC processor. Up here at the top we have general purpose registers, or general file registers. These are always 8 bits. And we have 256. That's a decimal number. We have 256 general file registers. And their addresses are from 00 through FF. But if we think of the address as being a 12-bit number, I'm going to write this as 000 through 0FF. And if I were to write this in binary, it would look like this.
That bottom one is supposed to be 0xFFF, right?
For the general purpose registers, it's just 0FF. There's still only 256 of these. But I'm just so, we've been saying this is the highest file register address. I'm just padding some zeros on the left. I'm going to change that in a second. All right, so these are general file registers. Now, it turns out on other processors, not the PIC 18F1220, but on other processors, there might be, 512 general file registers. And so there might be, something at hex 100 through 1FF, there could be a second bank of general file registers. Well, this does not exist on our processor. But, if we're drawing a memory map, the next chunk of locations in the address space would be, from 100 through 1FF. The next chunk would be 200 through 2FF, and so on. But none of that exists on the PIC processor. It's only got these 256 general registers. But if we keep going and we get all the way down to the end, and let me just fill in these addresses. So 100 hex looks like, a 100. 1FF looks like this. But if we keep going when we get all the way down here, the last 128 bits of this are going to go from hex F80 through hex FFF. And so F80 looks like this. Sorry. And FFF, there's our 12 ones. And these are the special function registers, or special file registers. So we can think of a 12-bit address, which means we have 4,096 locations we can specify. The first 256 are general purpose registers, the last 128 are special purpose registers, and everything else in the middle doesn't exist. All right, so that's the address map of our PIC processor. And you can see a picture of this in the data sheet, figure 5.6. And there's some extra information in here that we'll pick out in a minute. But, here's general purpose registers from 000 through 0FF. And they put an H at the end instead of putting a 0x in the front, but this means hexadecimal. And then
TR.
general purpose registers.
Oh.
Yeah. And then everything in here is unused until you get down here to F80 through FFF. Those are the SFRs, the special function registers. Don't worry about this bit yet. We're coming to that. All right. So we've got actually 384-ish possible operands. We can specify, one of these 256 general purpose registers, like, increment file register 20, or we could specify one of these special registers, which would be something like, clear F80. Or what we call port A. And if you look at the lab for the code for lab 1, there's a define statement here which says define port A to be 0xF80. And then down here it says clear F port A. Well, that says clear F 0x F80. So this clear F port A instruction is trying to clear the contents of a special file register. In particular, the special file register sitting right up here at the beginning of this bank of 128. All right, still with me? Okay, cool. We're getting somewhere good with this. All right. So here's the issue. When we specify an instruction, it's 16 bits, right? It's usually got, several bits for opcode, a few bits for other bits, and then we really have generally 8 bits to specify an operand. Well, if we only have 8 bits, how are we going to specify one of these registers if we need 12 bits to specify? Because if I only look at the first 8 bits, right, this and this look the same. But if I use 12 bits, right, this 0000 followed by 8 ones is a general register. This 1111 followed by 8 ones is a special register. They're totally separate creatures. So how am I going to specify a 12-bit address when I've only got 8 bits of operand? And this is where the access bit comes in. So the access bit is a shortcut. Because really we need 12 bits to specify an operand. We don't have enough space to specify 12 bits. So here's what we do. We specify as the operand these lowest 8 bits. Okay, that's the 8 Fs in the pattern for an instruction, right? We specify these as part of the instruction's binary coding. But then we use a trick to specify what these upper 4 bits are. Alright, so the goal is to be able to specify a 12-bit address without having to use 12 bits. And we do that using 1 bit, and that bit is called the access bit, or the A bit. And this is potentially confusing, but let me give you a picture of this, and I'll ask you to kind of take it on faith, but we can talk more about it as your curiosity demands.
So the 8-bit is kind of going to tell the CPU, hey, I need you to go, instead of using the general 8-bit registers, you need to take the last 8 bits and go to the special register.
Exactly.
Okay.
So the access bit basically answers the question, should we use the general purpose registers or the special function registers? All right, and here's the way it works. So if you look at this table, it's table 5, figure 5-6. When A equals 0, BSR is ignored, access banked is used. When A is 1, BSR specifies the bank used. Okay, so how do we translate this? Let's just say A equals 1. Okay, so if you specify an operand, and let me call it JKLMNOPQ. Let's say those are the 8 bits of your operand. Okay, so this is your 8-bit operand. Let me not be weird about it. So let's specify the operand. So F7, F6, F5, F4, F3, F2, F1, F0. Okay, that's your 8-bit operand. That's what you've coded inside the instruction itself. Okay, so if A equals 1, then the 12-bit operand is 4 zeros, F7, F6, F5, F4, F3, F2, F1, F0. So if you set this access bit to 1, then everything works the way that we've been pretending it works. When you specify something like, 0x20, that's the location you're going to increment, 0x20. No special function registers anywhere in sight. Okay, but if A equals 0, then the 12-bit operand is, well, it's not necessarily 1111. It replicates whatever this bit F7 is. So your 12-bit operand will be the following: F7, 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 F6, F5, F4, F3, F2, F1, F0. So most of what I've said is motivation for why this happens. This is really all you need to know, though. So when you code your instruction, if the access bit is a 1, then your 12-bit address is 4 zeros, followed by the 8-bit address you specified in the instruction. If your access bit is 0, your 12-bit operand is the most significant bit of your operand, repeated 4 times, followed by the 8-bit address of your operand that you coded in the instruction.
So for like port A, if A is a 0, you have the memory location XF80. It's just going to be 4 8s and then 80, or is it just going to be?
Yeah, you've got the right idea. So let's try to clear port A. All right, so let's come back in here.
Not gonna lie, I'm a little confused, but
Yeah, that's okay. That means you're close. So let's look at the coding for a clearF instruction. So clearF looks like a 0, 1, 1, 0, 1, 0, 1A, and then 8 bits of operand. All right, so I'm just taking that from the data sheet. So here's a clearF instruction. So if you wanted to clear port A, all right, go to your data sheet, find port A, and port A has address F80 hex. So we want to say clear file register F80. Okay, what would this be in binary? This would be so what's an F in binary?
15 or 4 1s.
Yeah, 4 1s. How about an 8?
1 and 3 zeros.
All right, and I'll do the 0. All right, so there's F80 in binary. So this is the address, the 12-bit address we want to clear. Well, if we set the access bit to 1, we cannot specify this address. If we set the access bit to 1, these upper 4 bits are going to be zeros. So what we want to do is we want to set the access bit equal to 1. And we know we want, these bits to be 0, 0, 0, 0. We want these bits to be 1, 0, 0, 0. And if the access bit is 0, sorry, 0, then these bits will be the same as whatever F7 is. So if I say clear file register 80, since that access bit is a 0, when the CPU turns this 8-bit number into a 12-bit number, what's this 8-bit number look like in binary? It looks like that. It's going to fill in these upper 4 bits with whatever that leftmost bit is, which is a 1. So if my access bit is 0 and I say clear file register 80, it's actually going to clear port address F80. So this is goofy. This is what you get with a RISC processor, right? Where adding 4 more bits to your instruction cranks the price of the hardware up to a point where you can't compete anymore. So you put the burden on the programmer to work with, you know, something like an access bit to keep the price of the hardware down, keep the size small, and so on and so forth. So this kind of thing happens all the time with RISC processors. It's a quirky mechanism, but it's a way to save hardware, basically. Instead of having a 12-bit address, we only specify 8 bits. And we use a trick to say, you know, do we want those upper 4 bits to be zeros or do we want them to be ones? If we want them to be zeros, just set the access bit to 1 and you're done. But if we want those upper bits to be ones, set the access bit to a 0. And as long as this bit is a 1, those will get turned into ones also.
So we can use hex F80 like you did with the defining statement at the top.
Mm-hmm.
It's just we gotta set the access bit to 0 when we want to use that port, right?
Right. And the good news is the assembler will do that for you. Right? We don't have to actually say, you know, clear port A 0xF80 and set the access bit to 0. The machine, the assembler will figure out for you that the access bit should be set to 0.
Would
So-
you say this specific version, because they're basically the same thing, just written differently, correct?
Sorry, say it again?
Both of these lines are basically just written differently, but are exactly the same thing.
Which 2 lines are we talking about?
That you just wrote. The clear F and the clear F OX 50.
Oh, yeah, right. Well, so let's go into our source code. So let's clear hex 80 and let's clear F80. And I'll compile these and I'll go to Window and debugging. My menu is off the screen for some reason. Output disassembly listing. Alright, there's our disassembly listing. So when we say clear file register 80, it cleared 0x80 and it said comma banked. When we said clear 0xF80, it said clear, it changed it to port A, right? Comma access. So the coding for these instructions was either 6B80 or 6A80. Right? The difference between 6B80 and 6A80 is 1 bit. Right? So 6B8, well, let's look at this. 6B80. So there's 6, there's B, there's 80. 6A80, there's 6, there's A, there's 8, and there's 0. And the only difference between these is this bit right here. Well, that's the access bit. So 6B80 is being coded with an access bit of 1. 6A80 is being coded with an access bit of 0. So if you look in here, 6B80 access bit of 1, that's the one that's clearing file register 80. 6A80, that's an access bit of 0, that's the one that's clearing actually F80. So there's a few levels of this, right? At the level of writing assembly language code in MPLAB, we don't have to worry about this. Okay, it's completely handled for us. At the level of trying to write machine code from assembly language, which you have some homework problems for, being able to convert, you know, an instruction like this or this into binary, we need to understand how to use the A bit. And a pretty simple way to do this is if you want to deal with a special function register, go ahead and set the access bit to 0. Because if we set the access bit to 0, we're going to end up with a bunch of 1s here. And if we're using a general purpose file register, set the access bit to a 1. And that will work, but it's a little more complicated than that. So if we go in the other direction, if we have binary for an instruction and we want to know what that instruction is doing, then we need to actually understand exactly what the access bit is doing. So there's some homework you can play with on homework 2, question 10, the one that we skipped from homework 1, is all about the access bit, and jumping in there will help.
Quick question.
Yeah.
On the other piece of paper where you had 6B80 and 6A80
Mm-hmm.
on the right hand, is that A bit just that one specific spot along those 4, the 1011 and the 1010?
Yeah, the A bit is right here. And the reason you know that is because if you look at that table 20-1 at the coding for a clear F instruction, this is what you see. It's going to start with 0, 1, 1, 0, 1, 0, 1, and then that 8th bit is going to be whatever A is. And so that's why that's where the A goes. And then these bits are whatever your 8-bit address are. So that's that bit pattern right there.
Insist, right? An access bit.
Probably not. I mean, in effect, the same kind of thing happens, but in CISC, you know, you might have an opcode that's, you know, 8 bytes long, like 60 bits or more, and you're usually not too worried about shaving off a bit here or there. So the mapping from a binary instruction to what it wants to do, to what operands it's working on, is usually a little more direct. But it gets into other layers of complexity where you have, you know, index registers and displacements and all kinds of things like that. And this is also more complex on other processors from Microchip. So, you know, as I said, some processors allow you to specify you know, maybe a general purpose register inside this bank of locations, right? So some PIC processors might have 512 general purpose registers and then 128 special function registers. And so same problem, if you only have 8 bits, how do you choose whether you're specifying from this chunk of 256 or this chunk of 256? And there's other things that kick in. There's something called the bank select register, which we don't have to deal with at all in this course. But the bank select register lets us choose which of these chunks of 256 registers we want to deal with. And that's something you find in you know, like an x86 processor. That's something typically called a segment register, for example. If your C program crashes and you get a seg fault, that's what it's referring to, is a fault in the segmentation of your memory and which segment you tried to access.
Interesting.
Yeah, we'll get into a lot of that in CSE 224. All right, so let me do one more thing, and then we'll go ahead and we'll take a break. So in lab 1, there were all these define statements. Define port A, F80, define port B, F81, define addcon1, FC1. And those are really symbols that, you know, were set up to allow us to do things like when we want to deal with addcon1, instead of typing in FC1, we can just say addcon1. Instead of typing in F81, we can type port B. So those defines are set up so that we can use mnemonics that are more meaningful to us, or will be, like port A, tris B, and so on, instead of hardwiring these magic numbers throughout our code. Right? Because what you really don't want is, you don't want to write code where every time I want to use port A, I've got to use F80, F80, right? And I've got to keep putting that through for a few reasons. Number one, magic numbers are error prone, right? If I'm trying to put in F80 every time I see port A and F81 every time I see port B, I'm going to mess up. And when I go back and I try to find what's wrong in my code, I just see F80, F81, FC1, FD2, you know, it all looks the same. So having these things defined once minimizes our chance of messing up. And if I wanted to take this code and port it to a different machine, well, on the machine I'm porting it to, maybe port A is now FB0. Well, I can change this one define statement, and my code will still compile just fine. So instead of embedding these magic numbers throughout our code, we define up front some symbols like port A, port B, tris A, and so on. All right. Well, those symbols are also defined for us, and so there's a file for us. It's called p18f1220.inc, and it's a bunch of stuff, but it's mostly a bunch of define statements. And so it defines things like port A and port B and so on. And so this is using these EQU statements. But this is where, you know, the fact that port A is F80, port B is F81, and so on, this is where these things get set up. And there's a whole bunch of things created in here that we'll use. And so when we write our code in assembly language, usually in the very beginning, we're going to do a statement called include, and we're going to say include p18f1220.inc. And that statement's going to set up all of our defines for us. And it's going to give us access to port A, tris B, addcon1, all this other stuff. All right. So please go ahead and send me an attendance check, direct message. Let me know that you're here, and we'll come back in about 5 minutes, and we'll start connecting hardware to software, which is where things start to get much more interesting. All right, and I'll be back in 5. think we're back. All right, so let's break out of the box. Let's look at how we connect this processor to the outside world. Because if all we're going to do is, calculate prime numbers or things like that, you may as well be using, an Intel processor. It's a lot easier to work with. The reason we're using microprocessors is generally because we want to interface them to some piece of hardware. We want to make them work with the outside world. So we want to read a switch, or we want to, drive a motor or something like that. So we've got to get in and out of the hardware, the CPU. And this is done using some of the special function registers, the SFRs. So let's start by looking at the pinout for this chip. And it's all simulated this summer, but we're going to pretend that we're working with an 18-pin chip. That's the one we normally use in the actual lab. And so 18 pins, all right, so pin 5, that's the ground pin. It's called VSS. Pin 14 is the power pin. That's where we put in our 5 volts. That's VDD. So we know what those do. And pin 4 is a reset pin. So MCLR, that's short for master clear. And it's got a bar on top, which means it's active low. So we usually pull pin 4 high through a resistor. And if we connect it to ground, it resets the processor. So pins 4, 5, and 14, well, those are pretty straightforward, right? That leaves us 15 pins. And most of these pins, if you look at them, they seem to have multiple descriptions. For example, pin 4, which is the main clear pin, also is something called VPP, and also something called RA5. Pin 1 is something called RA0, but it's also something called AN0. Pin 12 has 6 different functions: RB6, PGC, T1OSO, T13, CK1, P1C, and KB12. So this is also very common in RISC-type architectures. You find multiplexing or sharing of the pins. One pin usually has more than one purpose. Now the exceptions are the power pins, but even these, sort of have multiple purposes. This is the power supply, but also the analog power supply. But most of these, right, this could be an oscillator, it could be a clock, it could be RA7. This could be RB1, analog 5, transmit, some kind of clock, or an interrupt. So multiplexing of hardware. And so what this means is that before we can actually use these pins to do something like read a switch or drive a motor, we have to tell the CPU which pins do we want to use for what. Because, if you go to the data path diagram here, right? So here's some of the I/O systems. Here's some timers. Here's an analog to digital converter. Here's something for doing serial communication. Here's something for doing timing. Here's your ports that actually go to your pins, right? And we have to tell the CPU, hey, I would like to use pin 9 to read RB1. And I'd like to use pin 8 to read AN4. So you have to condition your pins. You have to set up, before you do anything, you have to set up what it is that you want to use the different pins for. So you've got to specify that. And so a lot of the stuff you see in the beginning of assembly language code is all about this initialization. And so clearing port A, clearing port B, putting a 7F into W and then putting that into ADCON 1, putting a 0 into W and then putting that into tris B, putting a 1 into W and putting that into tris A. That's all telling the CPU what you want to do with some of these pins. And it's kind of a whole separate task. You know, when we're writing a program, we're going to want to write a program to add 2 numbers in lab 2. But the first thing you're going to have to do in there is tell the CPU which pins you're going to use for what.
Quick question.
Mm-hmm.
If these are all pins, are we also saying that in this case we're also using the same pin twice?
Basically,
Or more than 2 times even?
so one pin can be used for more than one thing, but generally we're only going to use, within a program, we're only going to use pin 9 for one thing. It might be for RB1, it might be AN5, it might be TX.
So if your program requires you use one specific thing, let's say 5 times, does that mean we actually have to use 5 of those different chips?
If I understand your question, if, for example, we wanted to use RB1 and AN5, we would not be able to do that with one chip.
Okay.
And this could be...
So our programming, if it requires more than like 3, we would definitely have to use more than one chip.
Yeah, so for example, pin 9, one of the things pin 9 does is it allows serial transmission. So if you had an old style terminal that you can talk to, you know, through a 3-wire interface, you could transmit to it on pin 9, because that's what TX means. And you could receive serial information on pin 10. But if you also wanted to do something that required whatever KBIO is, right, you would not be able to do that. You'd either need a second chip or you'd need to do something in software.
So, I have a question.
Yeah.
So if you were to, say, use the RB0 pins, let's say, I don't know, for example, it's like a DB9 port you're controlling.
Mm-hmm.
It would change all the pins that are able to use RB0, RB1, RB6, all of them in tandem. Wouldn't it be like a flag or something that you check to put it in that mode?
I think that's what we're going to talk about next. So let me talk about port B and tris B, and if that doesn't answer it, then ask it again. But I think the answer to that is where we're heading next. And this gets into a kind of more general discussion tied into all of this, which is this notion of bytes versus bits. And when we write code in C, we think about, you know, X is an integer and Y is an integer. And if we want a flag that's going to say, you know, is it time to do something or not, we'll usually just use an integer. And we'll set it to, you know, 1 if it's true and 0 if it's false or something like that. Our processors are byte-oriented, right? The PIC is basically an 8-bit processor. Most things happen a byte at a time. But the granularity of these pins is really at the bit level. So here's a single pin. We can specify a single value called RA0. And we can make it high or we can make it low. We can make it a 1 or a 0. Here's another pin, pin 2, which is connected to something called RA1. Pin 6 is connected to RA2 and so on. Okay, so here's how these things actually work. There's a special function register called port A, and it's an 8-bit register. And each of those 8 bits corresponds to a single bit, right? And this bit is called RA7. This is RA6, RA5, RA4, and so on.
So in the lab when we were messing with RA0, messing with the one on the far right.
Exactly.
Okay.
Exactly.
Cool.
Yeah. All right,
I
so
was kind of wondering about that and how that was connected, and that picture just formulated a perfect connection.
cool, excellent. All right, so what do we do with this? RA0 pin 1. Pin 1 is basically tied to this least significant bit of port A. All right, and RA7, these are always a little tricky to find because they're not sequential. RA7 is right here on pin 16. That's tied to this most significant bit of port A.
So, quick question.
Mm-hmm.
If for lab 1, when we put in the stimulators for RA0, would it also have the same effect if we used AN0?
Probably, yeah. Could be an interesting new experiment, right?
Right.
Yeah, it should, because if you look at that file, and I already closed it out, but that include file that defines all of these things, RA0 is really just an abbreviation for 0. And RA1 is an abbreviation for 1. So AN0, yeah, would probably do the same thing because they're both on pin 1.
What does R and A actually define if 0 is just 0?
I think R is for register and A is A. And then RB0, RB1, those correspond to port B. But it's probably an interesting sociology study to figure out where some of these mnemonics come from. Because, at some point an engineer decides to start calling these bits RA7 through RA0, and they catch on, and that's what everybody calls them. And there's probably a reason somewhere, but there's a good chance that reason is lost.
So basically the reason that there is RA0 through 7 on this chip is you could design the code to feed bytes to other things on a circuit.
Mm-hmm.
That's the whole reason.
Pretty much, yeah. So let's build a circuit. So there's our 18F1220, and here's pin 1. And let's hook up a well-behaved switch. So we'll pull this up to 5 volts through a resistor. We'll have a switch that lets us connect it to 0. So by pushing this switch down, I feed a 0-volt signal into this pin. By opening the switch, I feed a 5-volt signal into this pin. So I can control whether I'm getting 0 volts or 5 volts, a logic 0 or a logic 1, into this pin. Well, if I connect this pin to 5 volts, if I'm feeding a logic 1 in here, and now I copy port A into the W register, and I look at this bit of the W register, it's going to have a 1. And now if I push this switch down so I have a logic 0 going in here, and I read port A again, this bit's going to be a 0. Okay, this is how our chip reads what's going on in the outside world. Any time that I read port A, this bit will be a 0 or a 1 depending on whether this pin is at 0 volts or 5 volts. I'm lying a little. I'm going to change this in a minute. But for now, right, this bit of port A shows me the voltage level being applied to pin 1 of this chip. And pin 2, which is labeled RA1, that's going to be tied to this bit. Now pin 3 is labeled RA4. If I put 5 volts at pin 3 and I read this port A register, I'm going to see a 1 in this bit, because this is the bit corresponding to RA4. And now if I ground out pin 3 and I read port A again, this bit changes to a 0. So I can read values from the outside world by connecting those values to certain pins, reading typically port A or port B, and checking a particular bit value.
Does it always have to read, or can it be an output as well?
Or we can do an output. And again, right, so if you look at this pin, there's a two-headed arrow on here. This pin can be an input pin or an output pin. Why? Because there's not enough pins to split them. Say again?
I was wondering about that.
Yeah.
Out of curiosity, would MCLR be our clock?
MCLR is the main clear. So that resets the whole CPU. But the clocks are usually oscillators, OSC, or clock CLK. The PIC processor actually has a built-in clock. So if you don't want to use something outside, you can just power this thing up and it'll start ticking. Which is pretty nice. It's like self-contained.
Cool. I've thought of a project idea with this thing.
Oh, cool. Awesome. Alright, so we can read voltage levels from the outside world by reading port A, but we can also write voltage levels to these pins. So for example, let me pick another RA. So let's look at pin 16. And I'm just going to label this, you know, this says RA7. I'm just going to put a little RA7 here to label that. If this is acting like an output pin, what happens when I write to port A? If I write a 1 in this most significant bit, all of a sudden this pin goes to 5 volts. And now if I write a 0 to this bit of port A, this pin goes to 0 volts. So if I want to set this output to be either high or low, all I got to do is write a value to port A where this bit, this most significant bit, is either a 1 or a 0. Pin 15 is RA6. Well, if I want to set that to be high, I write to port A and I make sure that this bit corresponding to RA6 is a 1. And if I write port A and I put a 1 in here, that pin will go to 5 volts. And if I write port A and I put a 0 in this bit, that pin goes to 0 volts. So if I've got this connected to an LED and a resistor going to ground, if I write port A and I have a 1 in this position, boom, my LED lights up. It's magic.
Quick question.
Sure.
Input and output, it's very indicative of where it's inputted and outputted in all of these because of the arrows. Does that mean that the programming internally is what's going to tell us what's going to be outputting where we want it to?
Mm-hmm. Yeah, you're going to specify as the programmer.
Just like everything's going to be outputting. It's going to be, you're telling it where you want it to output.
More or less, yeah, but it does get a little complex. So as a programmer, we have to specify what we want to do with these pins. And that includes specifying whether we want a particular pin to be an input or an output. Okay, but here's where it gets tricky, right? Everything is byte oriented. Suppose I say, suppose I want to write a 1, right, to pin 15. I want to drive that to 5 volts. Okay, so I could write a binary pattern to port A. Okay, so how can I do that in assembly language? Well, I can move a literal into W, and we can write literals in binary if we want. We can say a little b followed by a quote, and then we can write an 8-bit number in binary. So I could say 01000000. Alright, this will move this pattern of 1s and 0s in the W register, and then I can say move the W register to port A. And that will do this thing I've been talking about, which it'll take this pattern and send it into port A, and since this next to the last bit is a 1, That would put a 1 right here. That drives pin 15 to 5 volts. Our LED lights up. And then if I want to turn my LED off, I could do the following. Right, load in a different bit pattern where this bit corresponding to RA6 is a 0. When I copy that to port A, right, load in a bit pattern where this bit is a 0. When I copy that to port A, this bit becomes a 0. This goes to 0 volts, LED goes off. What makes this more complicated is that in my mind, I'm controlling this bit corresponding to RA6, right? But when I copy this to port A, I'm writing all 8 of these bits. In this case, I set everything to a 0 except 1. So in doing this move statement, I also forced a 0 into RA7, which pushed this down to ground. If I had a second LED on here, and I wanted both of these LEDs to turn on, I would have to use a different bit pattern. I'd have to use a bit pattern where both of these bits were 1s. But what if I'm supposed to be setting a voltage level on pin 3, right? I'm sending all of my pins to 0 volts except for these 2 pins corresponding to RA7 and RA6. So what I'm getting at here is in the assembly language, in the machine language of the processor, everything is done a byte at a time. But from the level of a designer, we're often interested in doing things 1 bit at a time. Right? This LED is a single bit in this 8-bit register. This switch is a single bit in this 8-bit register. And so we need to be able to interact with individual bits given these large hands that can only do things a byte at a time. And so that's going to be our next topic is how do we do things to individual bits when we only have the ability to operate on entire bytes.
So, going back to that lab one code again.
Mm-hmm.
If you're working with port A, as you defined it there,
Mm-hmm.
you're manipulating all 8 bits of RA0 through RA7.
Exactly.
Okay.
Which was fine in this lab because we only cared about 1 bit, right? But in other cases, it's going to be trickier because we're going to care about, multiple bits in here. And even worse, right? Some of these pins may be inputs, some of these pins may be outputs. So suppose, I write this pattern out to port A. Well, pin 1 is I think corresponding to RA0. I don't remember right now. But if I write a 0 out to this pin, but I've got this pin connected to 5 volts, is that a problem? Maybe. If I've got this switch closed, so this is connected to ground directly through a switch, and I write to port A and there happens to be a 1 here, which makes this pin 5 volts, I've got a short. I've got 5 volts coming out of this pin going to ground. I'm going to, burn something up.
Question?
Yes.
And it's mostly just to clarify something.
Mm-hmm.
Within this specific PIC 1851
Mm-hmm.
220, are we coding what's inside, or are we coding how we're building the exterior?
Can you elaborate on that question?
I mean, okay, because there are some pieces, I forget what they're called, the pieces that you connect to give it a 0 or 1.
Mm-hmm.
The connectors.
Right.
If they're both do you program internally whether or not it stops an incoming from happening and it's just an exterior, or is it set like that always?
So I think you're asking about the difference between input and output?
Sort of. I don't know how best to explain it, but I'm kind of wondering, like, we've been doing this code and telling how to toggle things and
Mm-hmm.
make things go to specific files and making the memory shifts. But I'm looking at here and going, this is a circuit. Wait a minute, have we been coding how we're supposed to be building this thing, or have we been coding what's supposed to be going inside of it?
So I think the answer is both. And that's part of what's cool about 270, right? Is that 250 we're really just dealing with kind of the hardware side, other than Verilog. We're really dealing with putting together resistors, gates, things like that. 270 and in general, when you're doing digital logic and microprocessors together, you're really doing both the software and the hardware. And we're writing code, but the code is generally interacting with maybe just switches and LEDs or motors, or maybe inputs to AND gates or flip-flops or things like that. And so our minds are kind of both inside the chip and on the stuff outside.
So if we're building this code for an interior and exterior, what if you're missing a specific component that you do put in the code? Can you just add it to the exterior to make up for what's lacking inside?
If I understand your question, the answer is yes, definitely.
Okay.
And this is, to me, like one of the funner aspects of engineering, right? Because you've got thousands of PIC processors to choose from. Which one do you pick? Or maybe you're given one like in this class, and maybe it's got some things it can do in hardware and some things that it can't, and so you have to write software to make up for that. Or you find some piece of circuitry to connect to the outside to make up for something that you don't want to code, and so on. All right, so let's talk about I/O. In particular, input versus output. And this is what these tris-A and B registers are about. So again, multiplexing. So 8 pins on port A that we could do input from, 8 pins we could do output on, 8 input and output pins for port B. That's 32 pins so far, just for port A and port B, just for simple digital input output. We've got 6 or 7 analog inputs available, so now we're up to 40 pins, right? We've got to share pins. We've got to multiplex. So one of the things we have to do is say, should we be using a particular pin to do input or output? And in this example, we were doing input on pin 1. We were doing outputs on pins 15 and 16. And so we wanted RA0 to be an input, and we wanted RA6 and 7 to be outputs. And maybe these other pins we don't care about. So let me redraw this. So this was RA7, RA6, and RA0. And this was pin 1. And RA6 is pin 15. And RA7 is pin 16. And the way we're building this circuit here, we want to do output on these pins. And we want to do an input. We want to read a voltage level on pin 1. And maybe we don't really care about these. Maybe those pins aren't connected to anything. All right, we need to tell the processor, hey, I want to use these 2 pins for output. I want to use this pin for input. Okay, we do that by setting up a register called tris-A. Tris stands for tri-state. And it basically says, should these pins be input or output? And here's the mnemonic that we use. If you want to do an output, we set the corresponding bit in tris A to be a 0. If you want to do an input, we set the corresponding bit in tris A to be a 1. And then these
Hold on,
we...
breaks real quick. You said tris stands for tri-state?
Mm-hmm.
Tri-state?
Tri-state is this third state of logic. So if you have an AND gate and you look at the output, usually it's high or low. It's a 1 or a 0. But some types of gates can be put into what's called a high impedance state. And these are called tri-state devices. So if you want to read a voltage level from this pin, you need to stop driving a voltage level to that pin. Or let's go the other direction. If I want to drive an LED, I've got to have circuitry inside here which says, hey, make this high or make this low. But if I want to read a voltage level that's coming in from a switch, I need to disconnect that internal circuitry. So I'm not driving it to a 1, I'm not pulling it down to a 0. I want to totally disconnect it. And that's something in digital logic we call tri-stating the output. So it's just a fancy way of saying we disconnect the output drivers from this pin and we say, hey, send a voltage in and I'll read the voltage level you're supplying.
Thank you.
Mm-hmm. So before we can use port A to do this, we set up tris A like this. Now we have to specify whether these are 0s or 1s, but we don't care what they are if we're not hooking those up to anything. All right. So 0 is for output, 1 is for input. How do I remember that? The beginning of out looks like a 0. The beginning of in looks like a 1. If you write like a lazy I. So output is a 0, input is a 1. So if I were to set tris A equal to, you know, maybe this, then I would be saying all of the RA ports are output pins except for RA0, which is an input. And so I would do something like move that bit pattern into W, and then move that bit pattern from the W register into tris A. And then if I wanted to read the value of this input pin, I could read from port A and look at this bit. If I wanted to set an output pin, I could write a bit pattern into port A, and it will drive those output pins accordingly.
So the same goes for port B. So if we're going to use port B and half of its inputs, half of its outputs, we need to set up tris B to tell which pins are inputs and outputs.
Correct, correct.
Okay.
All right, and like most things in this course, this will make more sense if you get in there and start messing with code. And you can play with outputs and inputs in the simulator. You can look at the variable tab to see output values. You can use the stimulus window to drive inputs, right? And if I set up this pin to be an output, if I set up this pin to be an output, if I put a 0 there, and I run it in MPLAB and I hit the stimulus on here, it's not going to read, you know, from that stimulus value because this is set as an output, not an input. Or if I set these pins up to inputs and then I try to write 1s into here, well, those 1s aren't going to go anywhere because these are not set up as outputs, they're set up as inputs. So you can sort of see some of this in the simulation. All right, and if you go to this table, 5.2, which summarizes the special function registers, if you look at, say, port A and port B, there's default values given. So if you look at tris A and tris B, default values are 1s. So is 1 an input or an output? Do you remember?
Input.
1 is an input, good.
Input.
So the default setting on all of these is to make these things input pins. Any idea why we would set the default to be input instead of output instead of random?
So that if you accidentally feed it a 5 volts, it's going to be okay.
Exactly. So suppose you're building a circuit like this, where I'm, feeding 5 volts into this pin, and my program starts to run as I turn on the processor. The program starts to run. Suppose the default value for tris A was to make this an output. Well, now I'm sending an output voltage here, which I'm also connecting to, you know, another voltage that's coming in. That could do some damage. So there's this notion of do no harm, right? And a lot of the default settings for these registers are the so-called do no harm state. So if I say that this thing should be an input and I've got it connected to an LED, that doesn't do any harm, right? I try to read from here. Well, you know, reading from an LED is a silly thing to do, but it's not dangerous, right? But if I have this pin connected to ground and I try to write a 1 into it, I'm going to create a short, and things are going to start to heat up inside my chip. So by default, your tris register sets everything to be an input. And then typically, if we want it to be an output, we change those to be zeros. All right, so what the heck do we do with all of this? So let's do an example. Let's make some code and hardware to control a fish tank. And we're going to start this today, and we're going to continue this on Thursday. So this will be an example we're going to build on quite a bit. We've only got about 20 minutes left today, but let's get started on this. And this will be a nice framework for us to explore several concepts, including probably the most important part of all of this, which is something we call bit masks. So let me give you a fictitious fish tank controller. So here's our PIC processor, and it's hooked up to power correctly and all that kind of stuff. And pin 8 is going to read a sensor. It's going to read a sensor called hot. And this sensor will let us know if the water temperature is too high. And pin 9 is going to be connected to another sensor, which is called cold, and tells us if the water temperature is too low. And pin 17 is going to be connected to a heater. Alright, so this is our first version of our fish tank controller. We have two sensors, a hot sensor and a cold sensor, and we have one heater. So if we just wanted to think about writing some code to make sure the water doesn't get too hot or too cold, and forget about everything we've been talking about for a minute, forget about ports and trisses and all that kind of stuff, let's just talk high-level design. What would a basic algorithm be to control the heater based on the temperature settings? And just think, you know, sort of plain English pseudocode here. Or pretend you're a computer, pretend you're the processor, right? You're babysitting your friend's fish tank, and you've got, you know, something that tells you if the water's too hot, something that tells you if the water's too cold, and you've got a switch you can use to turn the heater on or off. What is your algorithm? What do you do? Let's say you come by once an hour to check the fish tank. What do you do?
If cold is true, heater is true. If hot is true, heater is false.
Okay. If cold is true, set heater to true. If hot is true, set the heater equal to false. And then go back and do it again. Maybe we would read a book or something in between, but since the PIC processor doesn't seem to have anything better to do, we could just go back up and just keep doing this repeatedly. So there's a basic pseudocode for how we could use these two sensors and this one output to control the temperature of the fish tank, right? So part of this, eventually we're going to write, assembly language code, and we're going to get into trisa and part B and, increment this and all that kind of stuff. But before we get to the level of writing assembly language, we want to understand the algorithm that we're trying to implement as clearly as possible. And so this is something we call pseudocode. It's no language in the world that a computer would understand or a compiler would understand. But it's pretty easy for us to understand, right? It's human readable, and I drew a loopy arrow here to basically say go back up to the top and do this again. And a quick comment on gotos. So when we write code in C or Java or Python, right, we have for loops, we have while loops, we have if statements. We don't usually use a goto statement, right? Gotos, they still exist in C, right? They basically let you say, okay, I know you're executing instructions one after another, but right now I want you to go back up to this other section of code and start executing code from there. That's what this arrow is representing in here. It's just saying, okay, after you've done this if statement, go back up here, check this again. All right. Go ahead.
It's not something you can really avoid in a higher level language, but it's something you have to use at assembly level.
Yeah, we're gonna have to use gotos. There have been assembly languages with some structured support, but ultimately, when you write a for loop in C, it gets compiled down to something with a bunch of gotos in it. So we'll learn to love gotos, which are usually called branches or gotos. All right, so on Thursday, I want to make rigorous a way of writing pseudocode. I want to talk about flowcharting, which is a very specific symbolic way to write pseudocode. But let's just stick with sort of ad hoc pseudocode for now, and think about this heating system. All right, so if it's cold, then we're going to set the heater to 1. If it's true, we're going to set the heater to false, or maybe not. So how do we know whether this is 5 volts when it's too hot or 0 volts when it's too hot? And how do we know whether we turn the heater on by writing 5 volts to it or writing 0 volts to it? And we may think it's obvious, right? We may think that, if it's too hot, we're going to get a 1. If it's too cold, we're going to get a 1. If we write a 1, the heater will be on. If we write a 0, the heater will be off. But this has got to be specified. So if you were designing a system like this, or if someone had designed a system like this and you were trying to hook it up to your fish tank, you need to know those things, right? Otherwise, you risk like turning on the heater when it's too hot, right? So this is what you would do in a system diagram, right? You would make a system diagram, and you'd have an input called hot, and an input called cold, and an output called heater. And you would have to specify this. 1 equals too hot, cold, 1 equals too cold, heater, 1 equals on, 0 equals off. But you might find a heater where you write a 0 to it to turn it on and a 1 to turn it off. Or you might find that these things are what we call active low, where a 0 means it's too hot, a 0 means it's too cold. So we need to make sure we know what the meaning of these inputs and outputs are. And if you write this down once in the beginning, it will save you a lot of time down the road. Because, this may be pretty obvious, but there's going to be more subtle things in setting up your circuits that will flip around late at night sometimes, right? So writing this down somewhere up front and putting it in your lab report, right, will make a big difference down the road. All right, where are we? We've got about 10 minutes to go. Let's see, which way do we want to run this? We'll come back to this on Thursday. Let's take a little bit of a sidebar. Let's talk about how we test conditions. So to make a general purpose programming language, you need three things. You need sequential instructions. We've got that. We know our program just executes one instruction after another. We need a way to loop, and there is a goto statement, which will let us go back and execute code. So you need looping, that's your second thing, and you need a way to do conditionals. You need a way to test something and then respond based on the results of that test. And there's a lot of ways to do this on a PIC processor, but I want to describe one very particular way, and I'm going to ask you for this part of the course to stick to this as the way that you do conditionals. All right? So there's a branch instruction, BRA, it's like a goto. You can put a label somewhere in your code and you can say branch to that label, and it will jump back to that instruction. So like in my sample code over here, at the end of my code, I said here's a statement I call loop, let's copy port B into the W register, and I just said let's branch back to loop. So at this point it goes back to this loop label which says go ahead and move port B into the W register. So this is like a goto. The reason we have branches in addition to gotos though is because we can have conditional branches. So conditional branch or a conditional goto. And there's two that I want to look at. One is called BZ, which says branch if 0. And BNZ, which says branch if not 0.
Is it branch if thing in WERG or reg working register is 0?
No, although that would be cool. But yeah, that's a good question. Branch if what is 0? Branch if what is not 0? Right? If it's not the WReg, what is it that it's checking to see if it's 0 or not 0? And the answer is it's checking more or less the last thing that you did. So branch if the last thing you did gave a result that is 0 or that is not 0.
That's kind of messy.
It's kind of messy, but you get used to it. So for example, suppose I increment file register 20, then I say if branch if 0, you know, haha, and somewhere over here I've got a label called haha. Okay, what does this do? This takes the contents of file register 20, it adds 1 to it, writes it back into file register 20. If after that operation is done, file register 20 was exactly 0, this will be true, right? It will say branch of 0, it'll say, oh yeah, that last thing you did gave me a 0, okay, it's going to go ahead and it's going to branch to haha. If after you incremented file 20 though, if it was any value other than 0, 1, 2, 3, 254, 255, it's not 0, this branch does not happen, it just goes on to the next instruction after the branch. So in this case, this is basically saying if hex 20 is equal to 0, go to haha. But that's kind of misleading, right? It's whatever the last thing was that you did. So if I increment file register 20 and I store the result in the W register, right, then it's going to say, okay, so is the W register equal to 0? And it may not even be, you know, a result that I stored somewhere. So it's really just kind of whatever the last operation was that you did it result in a 0 or a non-zero value?
Is it if the operand was 0, or does it have something to do with the opcode being a 0?
It's whether the result of the operation was a 0. So there's no way by looking at the instruction that I can tell ahead of time if this is going to result in a 0 or not. It's when this instruction is executed, it reads the value of this register, which could be any number, right? It adds 1 to it. If after adding 1 the value was now 0, then this BZ is true and it'll take the branch. So it's looking at the state of the system after this instruction got executed. And we'll make that really specific next, but you get the general idea of the general sense of what this conditional branch is trying to do.
So basically it triggers a 0 flag. So if I were to make a instruction like increment so that a file register became 0 and then jump to the branch of 0 instruction, if I knew exactly where it was in memory and I jumped to it even though it wasn't sequentially down the line, it would still trigger it, right?
That's right.
Nice.
So if I had a number, well, that's just going to be a bad example. But okay, so yeah, so whatever the last instruction is that you did, if it resulted in a 0 and then you say branch if 0, it will branch. If it resulted in non-zero and you say branch if not 0, then it will branch. If it resulted in non-zero and I say branch if 0, it doesn't branch. And if it doesn't branch, this is what we call a no-op. It doesn't do anything, and it just goes on to the next instruction in memory.
Ops are great for debugging breakpoints.
Yeah, they are. All right, and this is not as random as it sounds. So if you go into your data sheet and you look at an instruction, so let's look at let's look at add literal W. All right, so add LW, what does it do? It takes a literal value K and it adds it to W and it stores the result in W. All of these instructions tell you statuses that are affected. And over here we see Z. Z means 0. So after you do an add LW, the CPU will remember whether the result of this instruction was 0 or not. And it remembers that by setting or clearing a flip-flop called Z.
That's like the carry bit.
That's like the carry bit. If you add two numbers, if you get a carry out of the most significant bit, this carry flip-flop is set to 1. If you don't, the carry bit is set to 0. If you do an arithmetic operation and the result is negative, then this negative flip-flop gets set. And if it's not negative, then the negative is not set. If you get an overflow, the overflow flip-flop is set. So all of these instructions adjust, some collection of flags. And they don't all update all of the flags. For example, when you AND with a literal, it only updates the negative and the 0 flags. It doesn't touch the carry flag. It doesn't touch the overflow flag. But the majority of these affect the 0 flag. A branch instruction doesn't actually change any of the flags. Right? Because the branch isn't actually doing an operation that, we could imagine does this result in a 0 or not. It's not modifying data. It's changing where you're going to potentially execute from. So for any instruction, you have to know what the statuses are that are affected to know whether you can use a conditional branch after those. And I want you to concentrate on BZ and BNZ. And those will be plenty for most of what we're going to do for now. But there's also conditional branches to branch on negative, to branch on a carry, and so on and so forth. And these flip-flops, these are stored in what's called a status register. And guess what? Status register is just another special function register.
Did you go in and hand manipulate them? Like if you wanted to take a literal from red and send it to the special register?
Yep, you can do that.
Interesting.
And there's reasons to do that sometimes. For example, if you want to do a rotate with a carry, sometimes you'd like to control what that carry value is that gets loaded in. So here's the status register, and these 5 bits correspond to the negative, overflow, 0, decimal carry, and carry bits. These upper 3 bits are unused. Right, and it's just another special function register.
Special register.
Say again?
Looks like reg itself is a special register too.
WReg? Yep.
Yeah.
Yeah, so that's another SFR. So the special function registers are where all the goodies are. This is where all the magic of the chip is. And some of these, you know, we don't actually care about. We may never have to deal with the status register directly. But, you know, it's stored in the bank of special function registers along with port A and port B and tris B and all those other things. All right, so if we want to, let's make one loop. Let's add the numbers 1 through 10 and figure out what that sum is. All right, so let's calculate a running sum of the first 10 integers. So you know, we'll define some variable where we're going to store this sum. So maybe I'll store the sum in file register 80. Doesn't really matter where you store it, but we gotta make a decision. So I'll store the sum in file register 80. I'm going to have a counter that counts. I'm going to go from 10 down to 0. So I'll make, you know, count. And I'll store that in, I don't know, file register 81. And let's write some code. We're out of time, so I'm going to do this really fast, and then we'll break this down on Thursday. But we could do something like this. So let's initialize our running sum to 0. Let's move a hex A into our counter. So count is the thing that we're going to add to our sum. Let's make a loop. And so how do we add count to our sum? Actually, so let's put our sum into W. Let's add W to file register count. And put the result back into the W register. And then put that back into the sum. So we're taking our count, which starts off at 10, we're adding it to our sum, putting it into sum. and then decrement our count. So our count started off at 10, now our count's going to be 9. And we'd like to go back and do all of this again unless our count got decremented to 0. So now I could just say branch if not 0, back to loop. So count will be 9, it will put the sum into W, it'll add 9, put that back into sum, decrement the count to 8. Keep going, and it'll loop here until count is 1. We'll add 1 to our running sum, decrement count. Now our decrement set the 0 flag, and when we say branch if not 0, that branch fails, and so now we're done. And we can do whatever we want. Maybe we'll copy the sum to port A or something like that. So this is, you know, a for I equals 10 to 1 loop, basically. And so part of what we'll be doing in coming assignments and homeworks is basically looking at ways that we can take the things we do in C with if statements, with whiles and fors and stuff like that, and break it down in this idea of small operations and conditional branches. All right, so we're past time. Cool, we still got everybody here. All right, awesome. I'm going to switch to my office Zoom, so come on in if you want to ask questions about lab or software and so on. If I don't see you in there, I will see you on Thursday. All right, thanks.
Thank you. Have a great day.
Thanks, you too.
Thank you.